So y equals 4 divided by x. So the inverse function is, well, basically, let's use the vocabulary you used. Let's make x the subject, or let's solve for x. Now, solving for x is not possible in this case because I haven't got a y value. I know, but we can go through the same process. So, what do? We've got y equals 4 divided by x. I want to make x the subject. So, first step is to multiply by x. So, let's multiply by x both sides. We've got x, y equals 4, and then divide by y. Okay? And we get x equals 4 over y. Now, do you remember last year having a discussion about the final step of this? So that is definitely how that is the function that I would use to solve y equals 4 over x. So for instance, if I knew that y was 23, yeah, I could put 23 in there and figure out what the x was. That would be solving it, right? So every time I want to solve this equation, if I'm given a value for y, I just do this, 4 divided by y. But when I want an actual inverse function, there is one final step. The actual inverse function is to write it as y equals 4 over x. Do you remember swapping the x and the y? Because if the input was x, the output's y. In the inverse function, the input is y and the output is x, but we don't do that. Inputs are always x's and outputs are always y's. Now you might notice something about that inverse function. Okay, do you remember what that is? It's then called a self-inverse function. And that's because the initial function and the inverse function are the same thing. Do you remember why it doesn't make sense to swap the x and y, really, if you're calling it specifically inverse function? Remember that discussion? Do you remember I said, well, this is fine, this is an abstract situation, but what if we put this in context? What if x was the amount of hours I work and y was the amount of money I get? Right, if I actually labelled that. So if I want to know how much money I get, I put how many hours I work in. It doesn't really fit with this kind of function, but that makes sense, right? And then if I swap it, and I've got x equals 4 over y, that basically says, well, if I've got this much money, this is how much I need to work, yeah? But if I swap the x and the y, what do I basically do? Yeah, I change the way I'm thinking about my cost and time thing. So when I put an inverse function in context, it doesn't actually make sense to swap the x and the y. Right? But when we're just dealing with abstract inverse functions with no real context, we would say swap the x and y. Do you remember the other notation for inverse functions? No? So if we say f of x equals 4 over x, the function that is applied to x is 4 divided by x. The inverse function is written as so it's the same thing, inverse. Right. So what I would say, the inverse function, or what we're actually doing is f of y is 4 over y, which would be the rest, but we don't see that, we don't use it, we kind of use this relationship. So there's a lot going in that very simple question, but the basic idea is that we do a solving process. Make sense? See lots of people writing it, some people haven't. Do I need to pause? Have a go at the next one then, while I'm pausing. So, we've got y equals 3 divided by x minus 1. First step to isolate the x. Solve for x. To make x the subject is 2. Oh, add 1. Good. So let's add 1 to both sides. We get y plus 1 equals 3 divided by x. Multiplied by x. Gives me x times y plus 1 equals 3. Divide by y plus 1 gives me x equals 3 over y plus 1. Final step, y equals 3 over x plus 1. So, if f of x equals 3 over x minus 1, then f minus 1, inverse function of x, is 3 over x plus 1. So just using both sets of notation. By the way, I think in the textbook, the methods they've shown, they swap the x and the y in their first step and say, right, now put it back to y equals. So I don't know whether that's something we prefer to do, but we could always do that with the next one, if we like. But it's something that we prefer to see. All right, let's do this final one, and then we'll have a look at how this appears graphically. Would you like to swap the x and y first step? Sure. Let's do that first thing this time then. So let's just make it x equals 3 plus 3 over 3 minus y. And now we've got to change it so that y is the subject. First step. Minus 3. Subtract the 3 from both sides. Gives me x minus 3 equals 3 over 3 minus y. Divided by 3 minus y. Should we do multiply by 3 minus y and then divide by... Should we do both of those in one go now? Because I think you might be spotting that when you've got this situation, it looks like they swap, right? So we're going to multiply by 3 minus y, and then we're going to divide by x minus 3 in one go, and we'll end up with 3 minus y equals 3 over x minus 3. And then, okay, subtract 3, okay, so if we subtract 3, we get negative y equals 3 over x minus 3 minus 3. Pardon? Multiply by negative 1. Or divide by negative 1, either way. And you get y equals 3 minus 3 over x minus 3. Okay. So in this case, f of x equals 3 plus 3 over 3 minus x. And the inverse function is 3 minus 3 over x minus 3. Okay. Alright, so just to address the graphing bit, let's just have a look. Look. So if I graph 4 minus x, well, what did we notice about 4 minus x? It was a self-inverse, right? So that means if it's a self-inverse, if I put a y equals x line in, it should be a reflection. The graph itself will be a reflection, yeah? Which, are we happy that that's a reflection around y equals x? So it makes sense that it's a self-inverse. All right, so switch that one off. The next one there, this is what 3 over x minus 1 looks like. And then we ended up with 3 over x plus 1. Yeah. And then we had 3 plus 3 minus x looks like that. And 3 minus 3. Okay, what do you notice? So that graph itself is already a reflection in y equals x. Therefore, although it doesn't look like it, these two must actually be the same thing. It's a self-inverse again, right? So this one was an interesting one, I thought, which is, well, they don't look the same, but can we show they're the same? Okay, so what can we do with these two functions? All right, so we're basically saying that 3 plus 3 over 3 minus x is the same thing as 3 minus 3 over x minus 3. How can you show that? Well, we could substitute a value in, but that is not good enough. Why not? That might work for the one value you picked, might even work for 10 values that you pick. But can we be certain that it's going to work with every value you pick? No. And that's a thing in maths, is when we start getting into proofs and things. Right? We can't just chuck an example in to show it is the same. We could pick one example and show they're not the same, right? So there is kind of proof by contradiction, by saying I can prove it's not equal, but that's not what we want. So we need to do some maths. It's not massively complex maths, but we just need to show those two are the same without picking any values, doing it algebraically. We could do that. Is there any way of ignoring this one and just showing that this one ends up being the same thing? Can I do something to this and show they are equivalent? Well, I think you're saying what Steph wanted to do, which was to kind of basically whittle it down until it says x equals x. But what I'm saying is let's now ignore that one is even there. Let's ignore that's even, let's ignore that's even there and pretend we've only got that and we want to do something to that and make it look exactly the same as that. Right? Multiplied by a positive one. Well, that's not going to do it, but you're along the right sort of line. I want, the way that we can do this is to look at this subtraction, and I've just been doing some work in my M2s about there is no such thing as subtraction. Subtraction is actually adding a negative. We probably did the same thing back when you were in M2s. Alright? So what if I were to write this as 3 plus a negative version of this? So we could make negative, and the negative in a fraction can be on the numerator or the denominator, right? So what if we take the negative out of here and put it on the numerator? So let's make it a negative 3 instead. that quite doing it? I'm not quite thinking of it. So, okay. No, sorry. I'm doing the negative, and then we're going to have the, if I take the negative of all of this, what must it be? So then it becomes 3 and 3 plus x. Okay. Does that work? Sorry, yeah, no, 3 minus x. X minus 3. I'm losing my track of thought. Right, how does that look at the moment? Right, so is this the same as that? Yeah?
Simplify it by making it 3 plus 3 over -1 times.
Okay, so I've now got this negative, I've managed to get the plus sign involved. I just need to put this negative onto either the numerator or the denominator to make it a negative fraction, yeah? Does that make sense? So I don't want a negative on the 3, I do want the negative down here, right? So if I take this negative, instead of applying it here, I apply it to the numerator, what does it become? It becomes 3 plus 3 over negative x minus 3, which is then 3 plus 3 over negative times negative 3 is positive 3 and minus x. Okay, so that's what we've got here. Same thing. Yeah, so we've now shown that those two are equivalent things. The second one was just written slightly different, which confirms what we saw graphing it, which is it was a self-inverse function. So it's not a surprise. Alright, so just to recap, back to those questions. An inverse function reverses you back to the initial value. Graphically, it should be a reflection of y equals x. Process of finding the inverse function is the same thing as making the x the subject or solving for x. Right? So that's a bit of a recap. It's nothing majorly difficult. One of the big things, standout things in this is you may well have self-inverse functions, which you see a lot of with rational functions. So, I bet you wish it was that. On your GDC, so if you can do it on your calculator, or not, or you do it on Desmos on your laptop, you're going to graph each function when it's inverse. Well, you have to do the inverse yourself. We've just done A, D, and E. You've got B, C, and F. The graphing is just to check that you have got a reflection in y equals x, so you see how I did that. And then find the inverse of each one of those. Just